Okay guys, so we covered the concept of changing area, and now this is only one of the three. We have angle, okay, another video that you can have, and the one that we're going to do right now is changing the current, and I want to give you an example. You see the presentation? So here we have, what is this? It's a drone of Amazon, and you want to deliver something to your house. But there's a problem with using drones, okay? So this is the vision of Amazon. You see this thing to send everything you order directly to your house with the drones. And this looks really cool, but there's a lot of problem doing that inside a really dense city. What is the main problem is that this drone can interact and found out that it would not be easy to get into a wire, electric wire, right? You need to be careful of that. But what electric wire actually is doing? A magnetic field. So this drone can actually sense this magnetic field and tell that everybody using Faraday law gonna see changing magnetic field and said, whoa drone, move on, change direction, because you're gonna enter inside a wire. So that's gonna be our next question. Let's do it. So we have here a wire. This is the wire. And what is the magnetic field that wire produced? Let's do it on red. If the direction of the current is that way, right? This is the current I. So the magnetic field would be, whoa, really strong here. Dude, really strong. Be careful. It's really strong here. Don't come with the campus, dude. This is really high magnetic field. But as we get far away, it's decreased, right? So this is the concept, right? And this happens in all space. So this is our drone, and our drone have a circuit, electric circuit. And this electric circuit have a resistance R, and have, let's give an axis here also. This is gonna be the x-axis, this is gonna be, hop, the y-axis, let's do it long. The y-axis, and I'm going to give you also the dimension of our circuit, okay, the control circuit that we have inside the drone. This is going to be our function yt, which is changing because this thing have a constant velocity. The drone is flying away, right? And this is going to be, this size is going to be a. So this term is actually yt plus a. And this term here, it's going to be the distance b, okay? So, sorry. I wanted this to be the x value of x. Okay? It's okay? So this is going to be the x value of x and y actually starting here. It's okay? Clear? Good. So this 0 and this is b. Small b. Okay? Great. Great, great, great. So first question, what is the location of the drone in time? What the drone is actually doing? What is the location of the drone in space in regards to time? So this is going to be section A, and I ask you what is the location of the drone, so you can say that this is physics 1 run, we are mature engineers, why you ask us these kind of silly questions, but I think this is important. So the location in space of this drone is actually, we know that it's moving in a constant velocity. So constant velocity multiplied by time, and don't forget to put where's the location you just started, drone, right? What I did here, I said that the change in time of this was the velocity, did integral on both sides, and got that. Good. So that was a really warm up for you. And so the second question is, what is phi b? And we're going to do the same thing we did previously. So if you didn't understand previously, don't worry. Let's do it again, okay? So we want to find phi b. What is the formula for phi b? Flux. You know fluxes. Flux is, first of all, it's an integral on an area, right? Right, good. And here we have the magnetic field dot, because the flux is a scalar. dot dA. Good. So what is the magnetic field that actually get inside our loop? What is it? What is it equal to? It's the classic magnetic field from a wire. Remember that? So this is a really important formula. So this thing is mu node I 2 pi 1 over y. And what I actually took here as an assumption, I said that the wire is really, really long, infinity long, which means that the size of the drone is really small compared to the wire, which makes sense. It's okay. Okay? If the wire is 100 times more longer than the drone, it could be a really good approximation, right? Good. Note that I didn't put 1 over r. I put 1 over y because this is the distance from the wire. Yes? Good. What is dA? Wait, what is dA? Not A. dA. dA is a small movement at the y direction and a small movement at the x direction. The camera see me? Yes? Small movement in y, small movement in x, and you want to sum up this kind of puzzle until you have all the area. So this here is dx dy, right? And now the integral is clear to me. So the integral is running respective to x, 0 to b, respective to y, from y. It depends where you started, right? But in general, it's starting in the position of the drone and how long is the drone plus a. Is that clear? I think this is the more challenging part. It's clear what I did here? I said the drone is starting at yt, the location where the drone is, and you need to sum all the small puzzles of dA until you get to ya. Okay? So that's what the loop look like. And does it change in time? Definitely. Okay? Note that the angle is 90 degrees. Woo, easy. Okay? Good. So these all are constants. Note that this current is the current of the wire, electrical wire, not our one in the loop. Okay? Good. So this one, if you're going to solve it, equal to mu dot I. The integral of x is really easy. It just gives us a constant b divided by 2 pi. Here you have in the integral y, and here you have y plus a, and inside the integral you have only this. And if you remember, this integral is an integral of logarithm, right? So it's the log, this one is logarithm. So we're going to get the result of this constant, right? This constant, mu I b 2 pi ln, upper limit is yt plus a, lower limit of the integral yt, and we know yt, we know that this one is actually equal to what? To logarithm of vt plus y node, vt plus y node plus a. Okay? So this is our malicious phi, right? A really challenging camera, see me? So this, I just did the integral, the logarithm, right? Put it, and this is a really malicious dt, but it's definitely changing in time. Definitely. And if it's changing in time, what I would expect to have in this wire? Current is correct, but before current comes the EMF, the voltage, the change in potential would make the charge go. Okay? So good. So before current we have EMF. And the formula for EMF, so this is part C of the question, EMF is equal to the minus dt of phi b. We just found phi b, right, as a function of time. So we just need to derivative it, right, to derive from that the real term. And it's really easy to take this logarithm and separate it apart. What do I mean? Right now I did the minus, right? This minus that, it's been division inside the logarithm, so it's going to be easier actually to leave it open like that. Minus ln vt plus y, right? It's going to be easier to solve it that way. So we have our constant here, IB, don't forget the minus, and we have the derivative of that. So the derivative of ln, just to remind you, the derivative of ln is if you derivative ln of some function, it's equal to the function derivative divided by the function itself, right? Should put here x. This is a general term, right? Good. So here we're going to end up with v, which is the derivative one, right? Divided by no derivative, the normal one, minus v derivative one. They have the same derivative. The only difference is a constant. Good. Yuck. But this is actually our EMF. This is the voltage that it's having, right? And if you want, there's going to be some emergency call for the drone, so we need some current that's going to be in use. So what is the current? How can I find the current? Can use. I have the resistance is given. We just found what is the potential difference inside the drone. Exactly, V over R. Good. This term going here, R is just a given constant, so it's taking this and divided by R, that's all. IB 2 pi R. Be careful, it's not the perimeter or something like that. It's 2 pi multiplied by resistance. Okay? Good. And here we have the same term that we had there. Okay? Good, good, good. So I want to ask you, okay, what's going to be the direction of the current? Let's go there. Let's go there. So which kind of current do I going to have going here inside the wire? In which direction? What's happened to the flux? As I'm getting far, far away from the wire and don't see it anymore. What's happened to the magnetic field? It's decreasing, right? It's becoming weaker and weaker, right? So if it's getting weaker, what is the current would try to do? Like friction, going to try to do the opposite, right? I'm going to try to enforce it, to increase it, to help you. Don't die, Phi. I'm going to be here for you. That's what he's shouting, okay? So the current said, okay, the excess are getting smaller. I'm going to give you more excess, dude. Don't worry about it. I'm going to give you excess. Don't die out, okay? I don't want to see any change. So the current must be at the direction. Is clear? So in that direction, to stop the change, okay? What I want you to imagine is, imagine Lorentz, Lorentz, the researcher, and what he's shouting, no, every time, okay? That's what he's actually doing. He tried to stop the change. He hates changes, okay? Is clear? So, last question, a quick one. So, I'm going to give you 3 scenarios, and I want you to tell me which one have the biggest phi b, okay? So we have the wire is here, one part of the location is here, the drone is right now here, and the drone is right now here, okay? 3 different cases. You know what, let's do it more symmetric. So here, and this is going to be that. Okay? So I'm going to draw also the magnetic field. So this is the case when it's completely centered. right? This one is weaker, white, smaller. This one, wait, the draw is not good. Okay, I'm gonna do a new one. Sorry for that. Okay, I want to really be careful in this drawing. So this is the wire. Case 1, the drone is in the middle. Case 2, the drone is about to leave the wire. Case 3, the drone is here. The magnetic field, this is case 1, this is case 2, and this is case 3. So the magnetic field here, big axis, big axis, big axis, right? Good. So here I have small axis, small axis, small axis, really small axis, really small axis, really small axis. Okay? And on the other direction I have this, 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 and this, 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 and this, right? So which one, what is the phi of this one? What is phi b of 1? Case 1 is equal to what? Think about that.
0.
Exactly 0. Because if I'm going to sum, oh, I got here a magnetic field in that direction multiplied by this area. Oh, but I have here the other magnetic field that would cancel it, right? So this one is 0, right? What's happened here? Phi b2, case 2. So this one canceling this one out, right? But I have some contribution. So I have something, right? And here in that case, they all gonna contribute to the phi. So phi 3. So if I would draw it even better, this question should be printed, okay? Because this actually took this part and this part, yeah? Only the first line is missing, right? So here I have this contribution, right? Which I have here, and more contribution here, right? Small axis. So phi b is for sure the biggest. The question was which phi b is the biggest and which smallest in size and magnitude. So you can say that phi 3 is actually bigger than phi 2, which is bigger than 0, which is phi 1. Okay? So this was the concept. So what's going to happen next? Okay? So the next question I'm going to send you by email, going to take care of the thing with the angle. Okay? How changing angle, and this is the reason motors actually working, right? In the same concept. And after we learn Faraday, we're going to learn a little bit more about the solenoid, which is the parallel idea to a capacitor. So we need to understand the flux really well in order to explain what's going on inside a solenoid. Okay? Good? See ya next time.